Hi everyone. In this video, we are going to talk about optical fiber communication. Fiber optic communication is a method of transmitting information from one place to another by sending pulses of light through an optical fiber. The light forms an electromagnetic carrier wave that is modulated to carry information. An optical fiber is a dielectric waveguide that operates at optical frequencies. This fiber waveguide is normally cylindrical in form. The functions of electromagnetic energy in the form of light to within its surfaces and guides the light in a direction parallel to its axis. The principle of light propagation through the fiber is when a light ray is incident on the interface between two mediums. Two mediums may be air or water having different indices at an angle greater than the critical angle. The light gets totally internally reflected within the medium of higher refractive index. Here actually we have shown a diagram with the N1 with a refractive index of medium 1 and N2 with a refractive index of medium 2. And phi is known as the incident angle and it is totally reflected back into the same medium with the same incidence angle. The refractive index of a medium is defined as the ratio of velocity of light in vacuum to the velocity of light in the medium. The propagation of light within an optical fiber is explained using the ray theory method. So when a light ray travels more slowly in an optical dense medium than in one that is less dense. Likewise, when a ray is incident at an angle of phi1, normal at the surface of interface between two dielectrics of a different refractive indices. That means, as I said, if one medium is air and another medium is glass, then the reflection occurs as shown in the figure. So here, actually we can see the incident light with this particular ray. First of all, it is actually refracted towards this medium called N2. And after when you just increase this particular angle, what happens means this particular ray, incident ray, will be refracted in this medium N2 with an angle of 90 degrees. So that is called as the critical angle. And when you pass the light ray more than this critical angle, what happens means this light which is incident on this particular normal point will be totally reflected back into its same medium, and that particular condition is called as the total internal reflection condition. And according to Snell's law, this particular total internal reflection can be expressed as N1 sin phi 1 which is equal to N2 sin phi 2. So when the angle of refraction is 90 degree and the refracted ray emerges parallel to the interface between the dielectrics, the angle of incidence must be less than 90 degrees. So here at an angle of incidence greater than the critical angle, as we said, the light is reflected back into the originating dielectric medium with a maximum efficiency of 99.9%. This phenomenon is called as the total internal reflection. So if you see the conditions for the total internal reflection, the first condition is the light which is incident on the dielectric of lower index from the dielectric of higher index. So this is the first condition that we need to satisfy. And the second condition is the angle of incidence should exceed the critical angle value. This is known as the acceptance cone. So the incident light which enters into the core of the optical fiber cable must be within the acceptance cone. Then only the light which is incident on the core will be reflected completely inside the core axis and it will travel through the core medium. If the light ray which is beyond this acceptance cone or beyond this acceptance angle will be refracted in the cladding and it will be lost in a few distances. So this particular thing can be expressed as theta in max, which is equal to sine inverse, where the N1 is the refractive index of glass and N2 is the refractive index of the quartz fiber. So here actually we can see the acceptance angle, that is, here actually the incident light enters at the axis of your core, and here actually it is totally reflected back into the core itself with the same incident angle theta c. And if you see this particular meridional ray, it will be reflected as the first angle, that is theta c, and it moves till the end of the fiber end. The next parameter that we need to consider is the numerical aperture. So numerical aperture is the one which is used to find out the amount of light which is traveling inside the optical core cable. So this can be expressed as numerical aperture is equal to n1 square minus n2 square. So once we know the values of the refractive indexes of core and cladding, we will be able to calculate the numerical aperture value very easily. Thank you for watching this video. Let's see more in the next video.